Hi everyone, welcome to this newest episode of Machine Learning Lectures. My name is Krish Chaudhary. My day job is as CTO and I'm a co-founder of Drishti Technologies at California, USA. And I'm proud to say we have been recognized as one of the top 50 AI companies in USA by Forbes magazine. I also moonlight as the author of the book Math and Architectures of Deep Learning from Manning Publications at New York. So, today we are going to talk about Gaussian mixture modeling. As such, I will assume some basic familiarity with probability, statistics, and of course Gaussian distribution, the basic form, some calculus. And if you really want to build up a step-by-step context on these things, then I invite you to go and take a look at my book, Math and Architectures of Deep Learning by Manning Publications. You can purchase it from the Manning Publications website. So, on to Gaussian mixture modeling. To introduce this, just to anchor our ideas, I will constantly talk about two separate problems. The whole lecture is kind of pivoted around these two problems. So the first problem is all of this pertains to a mythical town called Statsville. So in Statsville, there are males and females. In problem one, we are only concerned with them, adults. And we have height data of the adults of Statsville. In problem two, we are also concerned with children. So there are three classes in problem two, male, female, and children. And the problem is two-dimensional here. So we have height data and weight data. The things that we want to note first, the data is unlabeled. That is to say, in problem one, the height data, we do not know whether that particular instance of height belong to a male or a female. We just have a collection of potentially large number of heights. All we know are these are heights of adult residents of Statsville. And in problem two, we don't know whether it's coming from we have height pair of height and weight, and we don't know whether that height weight pair belongs to a male, female, or child. In fact, we are trying to build a machine which, in case of problem one, given a height, would predict whether that height belongs to a male or a female. This is not very realistic because height alone is not a good predictor of gender, but in this simple example, let's go along with that. And in problem two, given a pair of values of height and weight, we will try to predict whether that height-weight combination belongs to a male, female, or a child. Remember once again that the height and height-weight data respectively are unlabeled. That is, we don't know the class to which they belong. The second assumption is that individual distributions are Gaussian. Basically, this means that in problem one, the probability distributions of the heights of male and female Statsvillians are individually one-dimensional Gaussians. One-dimensional, the x-axis being the height and the y-axis being probability. And for problem two, this means that we will have two-dimensional Gaussians. Height and weight would be the independent variables, and probability, of course, is the z-axis. So these are independent. All of this is pictorially depicted here. If you will see, I hope you can see this properly. The diagrams are kind of so small, but essentially you will see there are two Gaussians. The blue one is female and the orange one is male, and they have separate mean and variances. they're two separate Gaussians, and they represent the this is the problem 1. So the top two figures, the top row corresponds to problem 1, and these are the separate Gaussians representing the probabilities of various heights of Statsville residents. And the right hand side, the second column, basically shows the sample point distributions. So in the one-dimensional case, you will see all the blue points corresponding to females are kind of clustered on the left side, and with a mean which is seriously to the left of the mean for the red points, which is corresponding to the males. So red or orange. And the bottom row corresponds to problem 2. Here you will see 3 Gaussians, and they correspond to male, female, and children. And of course, the space is two-dimensional because there are 2 independent variables, height and weight. And we see the corresponding point distributions. The center of the point distribution corresponds to the mean, and the fatness, the spread, corresponds to the variance. If you can recall your Gaussian, you will remember that in the multi-dimensional case, for example, in the bottom row, the variance not only determines the fatness, but it also determines the shape. Sometimes if the variance matrix is actually, let's say, diagonal, then this will be circular, the base will be circular. Otherwise, it might become elliptic. And you can see all of them here. So on the face value, this looks like a simple problem. You might say that, oh, what's there to it? I will, given an input height value, I will just compute the probability. Let's say I have a height value here. The probability of, I will go to the 2 density functions. I have the blue density function, and given and the value for that. For example, if I take this point where my mouse is, it corresponds to a more or less 0 value on the blue curve, and it's a non-zero, higher than 0 value on the orange curve, which is to say I have the probability of this being a female is lower than the probability of this being a male, and so this is a male. It's not so hard, it seems at first, right? And I can do the same thing in the two-dimensional case. I could take any point, and I could compute, I could plug that input value in the various Gaussian curves I have, and thereby I can obtain the probabilities of that input corresponding to any one of the classes, male, female, or child, and the largest probability is what I'm going to predict. But wait a second, we do not know exactly the PDFs, the probability density functions, right? We know they're Gaussians, but we don't know their mean and variances. Okay, so you say, okay, so we have to estimate them. We have to do function fitting, right? But then what function do we fit the data to? Fitting a Gaussian obviously does not make sense. Clearly the distribution is multi-peaked. Gaussians are single-peaked. The current distribution is a combination of Gaussians, one Gaussian per class. So obviously this is not a distribution which corresponds to, you can, a single Gaussian fitting a single Gaussian would not do the job. Which brings us to Gaussian mixture modeling. We have to basically, we will see that this leads to a weighted combination of Gaussians. That is what we will use to represent this sort of variables. But first, let me point out that what we are trying to solve here is essentially evaluating the joint probability. Now let X denote input and uppercase K denote the number of classes. In problem 1, we have only 2 classes, male and female. So uppercase K would be 2, and in problem 2 that would be 3 because we have 3 classes, male, female and children. We have also defined an auxiliary variable called Z. Why auxiliary? Because we have not any observation corresponding to it. It's kind of like a hidden variable. So its value is not observed as part of is not coming in as part of the input. However, this auxiliary variable essentially is going to represent class. We don't know how, we have no idea at this point how we are going to get the value of this, but it's going to represent class. So in problem 1, Z can take the value 1, meaning female, or 2, meaning male. And in problem 2, the auxiliary variable Z can take 3 values, 1 for female, 2 for male, and 3 for child. I have some typo here which I'll fix in the next edition of this lecture, but we'll just have to do with this now. So we are given this, essentially what we are trying to evaluate is the joint probability for a given input and a given class. In other words, the joint probability of the input random variable, which represents height or height weight pair, and the other variable being Z class, joint occurrence of those two. Let's study this a little bit more carefully. So let's take, so for the joint probability of a particular value of height in problem 1, particular value of height being h and 1, this is essentially the probability that the height is h and the class is female. Similarly, probability of h comma 2 is probability of height h and class male. And similarly for the problem 2, where the input will of course be two-dimensional, a height weight pair. So for instance, HW3, probability of that would basically corresponds to the class child. So essentially we are trying to find the joint occurrence of a particular input value and a particular class. That is the joint probability, and if we can evaluate that, from there we can solve our problem. So given a particular input x, if we are trying to find out if this is male or female, we will just have to check x, probability of x and 1, and also probability of x and 2, and see which one of them is larger, and we will predict that class. So using Bayes' theorem, this joint probability can be expressed as the product of the conditional probability of x given the class k and the a priori probability of the class k, as outlined in this top equation. I am presuming knowledge of Bayes' theorem. Once again, if you need more background in this, then welcome to my book. Anyway, so essentially I am expressing these in terms of the vector, whereas in the problem 1, really the input variable is not a vector, it's a scalar, but that's a minor distinction, so I will use these interchangeably. But the most important thing to note here is probability of x given k. This is essentially like for k, given k is 1, for instance, this means the probability of the probability distribution of females. For k equal to 2, this means probability distribution of males. We have already assumed that these are Gaussians. That was the starting condition of our problems. We already know these are Gaussians. Hence, the probability of x given k we have expressed as a normal. This is this calligraphy n stands for a normal, and if you remember your Gaussian, this is the formula for the probability. This is this kind of gigantic formula with exponential is what expresses the probability distribution e to the power something squared. This is how the probability distribution of a normal variable. This is the probability density function for a normal random variable. So the P of x given k is this normal density function. On the other hand, the probability of k, this is essentially the a priori probability of that class occurring without, irrespective of the input. As such, it is essentially, we can estimate it as the fraction of points upfront, even without knowing the heights or height weight pairs or anything. We can measure the number of in problem 1 we can measure the fraction of adult Stadtsville residents who are females, and adult Stadtsville fraction of adult Stadtsville residents who are males, and those are the a priori probabilities, and those fractions we express them as, we will use the symbol pi of k. So pi of 1 would be the fraction of females, and pi of 2 would be the fraction of males in problem 1. And similarly problem 2, pi 1, pi 2, pi 3. These would be, and these have nothing to do, these are independent of input, and those we can also estimate then. So we can estimate both px given k and pk, which means we can estimate the joint probability. Not sure why I am having this issue with moving to the next slide. So in attempting to solve this problem, we have come to the point that we have expressed the joint probability P of P, x and k together as a, look at the top formula, as a sum of products of basically a weighted sum of individual Gaussians. So the n, the calligraphic n, represents the Gaussian once again, and so my joint probability is a weighted sum. The weights are the pi's. They sum to 1, and my joint probability is a weighted sum of these individual Gaussians. If you remember, if we can marginalize, that is sum over all the values of k, all the classes, which would give us the probability of x. And that is the probability distribution function for Gaussian mixture model. There is a typo here, I'm sorry. This shouldn't have, the sigma should not have been there. This should go away. This is only the content of the sigma should be here. Anyway, so the probability of x is essentially a weighted sum of the Gaussian component probabilities. this is roughly what I was trying to say in the last slide. The overall probability of a variable which can belong to any one of a fixed number of classes, and each of those classes is itself a Gaussian distribution. That probability can be expressed by the formula shown here. It does make intuitive sense, doesn't it? That we have multiple Gaussians and we are basically selecting any one of them. And then our probability will be guided by that particular Gaussian. So that it's a weighted sum of Gaussians does make intuitive sense. So here I am trying to give a sense of the meaning of the individual components in that formula that we just saw. So in the particular case of problem 1, the summation is over 2 terms, and I have explicitly shown those 2 terms here. And the first term is essentially, once again, the pi1 is the a priori probability of female occurring, irrespective of the input. And if given that it's a female, what is the conditional probability of input x occurring, which is the second term. And their product gives us the joint probability of x and female. Similarly, the pi2 expresses the a priori probability of male. This is the normal, this term is the conditional probability of x given male, and their product gives us the joint probability of x and male. And in problem 2, there are 3 classes, and hence the summation has 3 terms, but the idea remains the same. Here I have shown various one-dimensional Gaussian mixture models. So the top left figure shows the component 2 Gaussians. They are in fact identical to the, for our problem 1, the probability of height distributions of male and female Statsville residents. And the green curve in the remaining 3 depict the Gaussian mixture model. Note that as we have different pairs of pi, the pi is always sum to 1. So if one of them is given, the other one is kind of determined. But if they're both 0.5 and 0.5, then you get this kind of a Gaussian. The green curve here indicates a Gaussian mixture model which has equal values for pi. Here the pi's are different, and pi1 is significant, is 0.7, and pi2 is 0.3, which is why you see a much taller peak for the left side, the one which matches the female portion, and a much smaller value. And this is a smaller value for the male portion, the right hand peak. This is exactly the reverse of that. This shows GMMs in 2-dimensional. These are with circular bases. Once again, you can observe that the hill heights depend on the pi's. In this case, the 2 pi values are equal on the top left, and they're unequal, in one of them being larger. Sorry, the top left figure are the 2 component Gaussians, and then we have various combinations of pi values depicted here. So what we have found out is that given such a situation where effectively I have multiple classes. Each class follows a Gaussian distribution. I can represent my output variable as a Gaussian, but I still haven't quite solved the problem of, given a set of input values. For instance, in problem 1 I will be given a set of height values only, nothing else, and in problem 2 I will be given a set of height and weight pairs, nothing else. Given these, how can I actually determine the GMM? Determining the GMM essentially means determining the mu values, determining the variance values, and determining the pi values. If all these three are known, I know the GMM, and then as we saw just now, we can actually we can actually solve the problems. That is, know the probability of a particular input belonging to a particular class. We can find out that probability, and we can predict a class by identifying which probability is highest. So this algorithm, it's called GMM fit. It's also known as expectation maximization algorithm. It's called EM algorithm, and EM stands for expectation maximization, and it also runs kind of in a pair of steps that keep on alternating. Unfortunately, there is no closed form way of identifying the mu, sigma, and pi values for a Gaussian mixture model. We just have to iteratively process the data in again and again, and this is the only way, unfortunately, because my book has a long section kind of giving many insights into why this is the case. However, here we will just kind of accept the fact that we have to do a iterative relaxation algorithm. We start with some random values for these unknowns. Then we will alternate the E step and M step, and then again the E step, and then again the M step, and we will go over like that. In the E step, we compute this quantity, let's call it the gamma. The gamma is essentially, it can be shown that it is representing the probability of the kth class occurring conditioned to the occurrence of the ith input, that is gamma sub ik. So we compute, note that gamma of ik contains all pi, sigma, and all the unknowns. And then, so in order to compute gamma, we need to know the value of the unknowns, and then we update them using gamma. This is why it's kind of a circular loop. This is why it's called relaxation. You use to compute, you use the present value of unknowns to compute a set of auxiliary variables. Using them, you update the unknowns, and then again keep doing that. Eventually, though, it can be proved that this technique will, in every iteration, it improves the approximation. Remember, we started with random values. In every iteration, it improves the approximation by just a little bit. So if we keep doing this sufficient number of times, eventually we will converge to some good values. That can be proved. Although that is a little bit of a red herring, because it doesn't say after how many iterations. So in real life, whether you will converge to good values or not is somewhat up to luck. So we basically keep on iterating until you are happy with the results. Which leads me to the conclusion. We have taken a shot at getting some insights into Gaussian mixture modelings. One thing that needs to be emphasized is these are unsupervised methods. That is to say, we do not need labeled data. Labeled as in, for example, think of problem 1. We got a bunch of heights, but we did not know whether the height values belong to male or female classes. So this belongs to a particular class of modeling called unsupervised modeling. And similarly, they actually help us in a particularly tricky situation where there are multiple classes. Yes, we are making the assumption each class is a Gaussian, which is not such a bad assumption to make in many situations, but this gives us a more complex variable, which is in some sense a combination of the Gaussians. Thank you. There is a lot of code. If you look for in GitHub for math and architectures of deep learning, you will see the code for all GMM. I think it is not published yet, but it will be published shortly. Thank you for taking this course.